In this video, we're going to take a look at exponential functions. So in order to find and deal with exponential functions, we need to start out by dealing with exponents themselves, and in particular, exponent calculations. When we have an exponent, we're having a number raised to a power. That number, which we generally write as b, is called the base, and the power, or the exponent, is p. Let's do some calculations and see how this goes. We can do the calculations by hand, or we can utilize some calculator techniques. We'll mix and match and do a little bit of both. Now, I'm assuming we know a little bit about exponents. 5 to the third power is like 5 times 5 times 5, which I can type in on my calculator. I can also type in on my calculator 5 raised to the third power. We've done that when we were dealing with polynomials and plugging in numbers into polynomials. We get 125. 0.2 raised to the third power is similar. I take 0.2 times itself 3 times, or in the calculator, I can just take 0.2 and then caret 3. So we can do that, and we get 0.008 when I do that. Now, 5 to the negative third, that's a different calculation. If we're doing a negative exponent, you can do it by hand by realizing that this is like the reciprocal 1/5 being raised to the third power. So a negative exponent is like the reciprocal being raised to a positive exponent. If we had to do it by hand, we do it that way. If you do it on your calculator, it's perfectly fine to input a negative number into the exponent in your calculator. In this case, I also get 0.008. So notice that 0.2 raised to the third power and 5 raised to the negative third power were the same thing, because 1/5 as a fraction is the same thing as 0.2 as a decimal. 3 to the 0.5 power, we can plug that in on our calculator. We get approximately 1.73. That's not an exact value. The reason we get about 1.73 is that 3 to the 0.5 is the same thing as 3 to the 1/2 power. And it turns out that is, in fact, the exact same thing as the square root of 3. The square root of 3 is 3 raised to the 1/2 power. So all of these things are equivalent: raising to the 0.5 power, raising to the 1/2 power, and taking a square root. So when we have fractions in our exponent, we can use roots to get those things calculated. We can also just plug them in into our calculator. Now, when we have 2.6 raised to the third power, that's like the same thing as 2.6 times 2.6 times 2.6. When you do that, you get 17.576. When you raise 2.6 to the 3.2 power, well, you can do this by hand if you want. It's a little bit more difficult because 3.2 as a fraction is 16 over 5. So this is the same thing as 2.6 raised to the power 16 over 5. And I can actually rewrite that with roots. I'd have to do a fifth root of 2.6 to the 16th. That's difficult to do. Instead of doing that, I'm just going to type this into my calculator. 2.6 raised to the 3.2 power is about 21.28. I'm rounding to 2 decimal places with that value. And then even with something like an irrational exponent, we can plug this in. We can plug in an irrational exponent into as the exponent in our calculator. And that's perfectly fine as well. We get approximately 20.12 in that case. So we can plug in any exponent that we want when my base is something like 5 or 3 or 2.6. And even if we don't know the exact value, even if the exact value is an irrational number, we can at least get approximate values. Now, in all of those previous cases, our base number was a positive number. What if we had a base number which was a negative? Well, if our base is negative, that's going to be okay if we raise it to the second power or the fourth power or even the 17th power. But what's going to happen when I raise it to the 0.5 power? What's going to happen when I raise it to the 5.2 power or to the pi power? Let's calculate these on our calculator. So when the exponents are whole numbers like 2, I don't get a problem. By the way, when you're typing this in, make sure you're typing this in with parentheses around the -5 and the exponent on the outside. If you forget the exponent, then we have, or excuse me, if you forget the parentheses, we have a different order of operations. So -5 raised to the second power gives me 25. When I raise that -5 to the fourth power, I get 625. If I raise it to the 11th power, I'm getting -488,28125. And if we put in the parentheses, you can see that's -48,828,125. So whole number exponents are perfectly fine to type in to the calculator. Also, if you put in something like -2, so if I change this from a +2 exponent to a -2 exponent, then that's just the reciprocal, so -1/5 raised to the second power, and that's perfectly all right to calculate as well. You get 1/25 or 0.04 as a decimal. So integer exponents are perfectly fine. However, rational number exponents are not. If you try to type in -3 raised to the 0.5 power into your calculator, what you're going to get is something that doesn't work. It gives you a non-real answer because this is taking the square root of -3. And so this is a non-real number. And that causes a problem if I try to graph, or excuse me, if I'm typing that in on my calculator. The same thing is true if I have an exponent of different values. So if I took 3.5 instead of just 0.5, you would get a non-real number. Now, this doesn't mean that every single irrational, or excuse me, every single rational number can't be calculated. In this one, -3 to the 5.2 power can actually be calculated. That's about 302.71 according to the calculator. And what they're doing there is they're taking 5.2 and rewriting it as 26 over 5. And so what they would do is they would take a fifth root of -3 and then raise that to the 26th power. It's perfectly okay to take a fifth root because that's an odd number. It was not okay to take a square root because that's an even number. Now, on the other hand, if we take something to the pi power, this also is a non-real number. Okay, -3 raised to the pi power, that's a number that's not real. So the point here is that while some exponents will work if our base is negative, not all exponents work when our base is negative. A lot of times we end up with non-real numbers. So if we have to do exponential calculations, like I said, with that 26 over 5, as long as our base is positive, we can always do the exponential calculation this way. We can take the dth root of b to the nth power, or the dth root of b and then raise it to the nth power. I'm saying n over d is numerator divided by denominator. So the denominator's root and the n is my exponent. And if the base is positive, then all of these are equivalent. But if the base is negative, sometimes I can't calculate it. By the way, if the power is irrational, then there's no nice way to rewrite it. We can still calculate the number if the base is positive, but if the base is negative, there's really no way to calculate it if my power is irrational. So I just have to do that operation. So now we look at the concept of an exponential function. An exponential function is a function that can be written as f of x equals a coefficient times b to the x power, where x is a variable. A and b are going to be real numbers. And because we get a little bit sticky when our base is a negative number, we're going to force our base to be positive, and we're going to force our base not to be equal to 1, because 1 raised to any power is just 1, and so the exponent doesn't do much there. So we're going to force our base to be positive so we avoid those weird negative base situations which end up with non-real numbers. But that's an exponential function. The key thing is that the variable is in the exponent and the base is going to be a positive real number. I'll have a coefficient of a real number. The coefficient doesn't have to be positive. It can be anything you want. So let's take a look at these functions here. 4 to the power x, x to the power 4, and 3 to the power 2x minus 5. Are these exponential functions? Well, this first one is. This has base 4 and a variable in the exponent. So this first function is an exponential function. This second function is not exponential. While we do have a base and an exponent, the variable is in the base and in this case, the number 4, the integer 4, is in the exponent. So that is not an exponential function. This last one takes a little bit of understanding of how exponents work to figure out that this one is an exponential function. Let me show you how I know that. So the reason I can say that 3 raised to the 2x minus 5 is an exponential function is because of the rules of exponents. The rules of exponents say I can rewrite that as 3 to the 2x power multiplied times 3 to the negative 5th power. I'll bring that 3 to the negative 5th power up front. That 3 to the negative 5th power is 1 over 243. So that's going to be 1 over 243 multiplied times 3 raised to the 2 times x power. One more rewrite does it for us. It turns out that 3 raised to the 2 times x power is like a base raised to the x power. So I get 1 over 243 multiplied by 3 squared, all raised to the x power. So that's like base of 9 being raised to the x power. Hopefully that all makes sense. So this makes our function in the form, this puts our function into the form of our standard exponential function form. A times a base raised to the x power. A is this 1 over 243. Our base is 9 raised to the x power. Now, generally speaking, we don't have to do all of this work to show that this actually is an exponential function. As long as I have a base, which is a numerical value, and as long as I have a variable in my exponent, then we, in general, say we have an exponential function. So my base is a real number, variable in an exponent, then we consider that an exponential function. And we won't do all this rewrite most of the time. Once we can recognize what an exponential function is, we can do some calculations by plugging in some inputs and finding some outputs. We have f of x is equal to 2 times 1.04 raised to the x power. It asks us to calculate f of 3, f of negative 5, and f of 19.1. Let's go ahead and do that. When I do my evaluation, generally speaking, I'll just type these into the calculator. We'll have 2 times 1.04 raised to the third power when I plug in 3. That gives me a big long decimal, and I will round that for the sake of this video to 2.25. When I plug in a -5, I end up with 2 times 1.04 raised to the -5 power, and that gives me about 1.63. Oh, I'm sorry, 1.64, excuse me. So there we go. I can do the same thing with the power of 19.1. 2 times 1.04 raised to the 19.1 power. If you're doing this by hand, you have to take the exponent first and then afterwards multiply by 2. Your calculator should do that automatically, and this gives me a value of 4.23. Notice that as the exponents got bigger, we were ending up with larger numbers. So a 19.1 gave me a 4.23. And with an exponent of -5, we got a smaller number, our smallest number that we saw anyways. The reason for that is that our base is above 1. If our base is above 1, then we'll see growth in the exponential function. So as you plug in bigger numbers, your outputs are going to be bigger. If your base was less than 1, then you'd see the opposite. You'd see as you plug in bigger numbers, you'd get smaller output values. Let's do another example. Let's take g of x and set it equal to 2.3 to the x power. And then let's plug in root 5. By the way, the square root of 5 is a little bit over 2, but we'll plug in square root of 5 exactly. We'll plug in a -2.3, and then we'll plug in a 0. If you want to do this on your own, push pause on the video and find these outputs on your own. All right, I will do these. When I plug in the square root of 5, I get 2.3 raised to the square root of 5 power. This is something you can actually just plug into your calculator. You just take 2.3, hit the exponent key, and then hit the square root key, and then hit a 5. And it's not going to give a nice value because it's going to be an irrational number. You get approximately 6.44 when rounding to 2 decimal places. I can plug in a -2.3 into my function. We'd get 2.3 raised to the -2.3 power. Again, this is not going to be a nice whole number value. You get about 0.15. Notice that raising to a negative power just gave us a really small number in this case. When I raise to the 0th power, 2.3 raised to the 0th power is 1. That's a rule of exponents you probably should know. When you raise anything to the 0 power, you end up getting 1. Once again, raising to bigger powers gave us larger outputs because our base was above 1. Anytime we have an exponential function, we can actually start with the base exponential function. So just our basic f of x equals a base to the exponent of x. Like we had in our previous problem, we had base of 2.3 raised to the power of x. Well, our base exponential function is going to have some nice properties. We say that 1 is the initial value of that function. Initial value means that when we plug in 0, we get 1. That's because anything being raised to the 0th power is 1, so long as, again, our base is positive, and then we usually always say our base is not equal to 1. So as long as our base is positive, anything raised to the 0 power becomes 1. Also notice that if we put in the value of x equals 1 as our input, then we get b to the first power. So f of 1 is going to be equal to b to the first power, or just b. Similarly, when we plug in a -1, we end up with the reciprocal of b, 1 over b. Now, the nice thing about using bases which are positive is that our domain becomes all real numbers. And the range for this function, the output values, are going to be anywhere from 0 up to infinity. So it's going to go from 0 all the way to infinity. Again, this is 4 exponential functions where the base is greater than 0. So exponential functions, the base here, whose base is greater than 0, are good. Every exponential function like that is going to have these properties. Let's actually graph these exponential functions. I'll do this on Desmos. I'll graph f of x is equal to 3 raised to the x power, and then I'll graph g of x is equal to 1/3 raised to the x power. These are both base exponential functions. The first has base of 3. The second has base of 1/3. Here we're looking at the graph of f of x is equal to 3 to the x power. Notice, like I was saying, the base there is bigger than 1. And so as we move left to right, the function is increasing. And as you move more and more to the right, the function is increasing at a faster and faster rate. Also notice that it goes through the point 0, 1. That's because when you plug in 0, you get a 1. And it goes through the point 1, 3. That's because when you plug in a 1, you get a 3. By the way, if you plugged in a -1, you would get a 1/3 as the output. In decimal version, that's 0.333. So we see f of x equals 3 to the power x. As we move towards the right, we increase, we shoot off towards infinity. Notice what's happening as we move towards the left. As we move towards the left, we get closer and closer and closer to an output value of 0. In fact, if I put my cursor on this point here, like -30, it'll show an output value of exactly 0 because it would round it to that number if you rounded to a few decimal places. But that's what's happening. So to the right, it's shooting off towards infinity. To the left, it's going down towards 0. Notice we never get a negative number because 3 raised to a power never becomes a negative number. Now, what's going to happen if we take our base to be 1/3? It turns out that when we graph g of x equals 1/3 raised to the x power, we essentially get 3 to the x, but flipped around the y-axis. So everything works in reverse now. As we get smaller inputs, it shoots off to infinity. As we get larger inputs, it gets closer and closer and closer to 0. We're still going through the point 0, 1, but now we go through the point 1, 1/3, and -1, 3. Now, that is not coincidence why these two graphs look identical but flipped around the y-axis. The reason that is true is because 3 to the power x, or let me rephrase this, is because 1/3 to the power x is the same thing as 3 to the negative x power. And that's just the transformation. When you replace x with a negative x, that's the transformation of flipping across the y-axis. So if our base is somewhere between 0 and 1, we're going to have the general look where to the left it shoots off towards infinity and the right it approaches 0. If our base is above 1, then as we move right, we shoot off towards infinity. And as we move left, we approach 0. With that information, we can actually look at the graph of a function and pretty quickly determine that if the function is one of our base exponential functions, we can determine the base on that exponential function. Notice that we're going through the point 0, 1. As we move towards the left, we're getting closer to 0. As we move towards the right, it looks like it's shooting off to infinity. Also, it looks like this function goes through the point 1, 2.5. Knowing that it goes through 0, 1, knowing that it has this shape, and knowing that it goes through the point 1, 2.5, that means my base needed to be 2.5. So just by looking at this graph, I know that this is the graph of the function f of x equals 2.5 raised to the x power. By the way, the reciprocal of 2.5 is 0.4, and it does look like this graph also goes through the point -1, 0.4. Might be hard to see exactly if this is like a 2.5 or a 2.52, but it does look approximately like it goes through the point 1, 2.5. Let's look at the graph of another base exponential function and try to figure out what the base would be for this graph. Push pause on the video if you want to do this on your own. In a couple of seconds, I'll show you it. All right, so this one shoots off as we move towards the left and goes towards 0 as we move towards the right. So I know that the base is going to be somewhere between 0 and 1 because of the general shape. Obviously, it goes through the point 0, 1. It also goes through the point, it looks like 1, 0.25. This is segmented in 4 sections. If you ever are in doubt, think what's the reciprocal of 0.25? The reciprocal of 1/4 is 4. So if I plug in -1, Does this go through 4? It looks to go through 4. So plugging in -1 gives me a 4. That means the base needs to be the reciprocal of 4, which is 1/4. So this is the graph of f of x equals 1/4 to the x power. Hopefully that makes sense. Our base exponential functions can be identified if we're given the graph. Now, the reason we started with our base exponential function is because after that, we can do horizontal shifts and vertical shifts. We can flip across the y-axis. We can flip across the x-axis. We can do vertical stretches, horizontal stretches, all of the same transformations we had in previous sections. Obviously, the one we saw before was when we multiplied by a coefficient of a. If I multiply by a coefficient of a, then all we've done is change the initial value to a. When you plug in a 0, b to the 0 power gives you 1. 1 times a is a. And therefore, the y-intercept is 0, a. The domain is still all real numbers. The range is either going from 0 to positive infinity if a is a positive number, or it goes from negative infinity to 0 if a is a negative number. Because if a is negative, then this represents a flip across the x-axis. I bring up this transformation in particular because this is one that we'll see a lot. Just having a coefficient out front of my base exponential function. So let's take a look at these two functions and see how they're transformed from our base function of f of x equals 3 to the x. Now we've already graphed g of x equals 1/3 raised to the x power, and we saw that was a flip across the y-axis. So like we said, the reason that g of x was a flip across the y-axis is because 1/3 raised to the x power is just like 3 raised to the negative x power. And so remember, when we replace x with negative x, that's a flip across the y-axis transformation, and then we're done. This h of x should be moved, right 2 units, should be the f of x moved right 2 units and then up 4. The x minus 2, that's the transformation of a right shift by 2, replacing an x with an x minus 2 is shift right by 2. And then when you add 4 at the end outside of the exponent, then we're moving up. Let's confirm that by graphing. We've already confirmed that g of x was equal to 1/3 to the x power, was a flip across the y-axis. We already saw that. So now let's just confirm that h of x is a shift right by 2 and up 4. I'm going to be looking for this initial point that is at 0, 1 to go to 2, 4 if I'm right. And sure enough, 0, 1 shifts up, shifts to the right and up. I shouldn't say 2, 4, excuse me, 2, 5. So shifts right 2 units and up 4 units, which brings me to the point 2, 5. Okay, So my initial 0, 1 got moved right 2, up 4, which gets me to the point 2, 5. So that's it. So you can see that these shifts are the same types of transformations we've dealt with earlier. This is just the intersection point. Don't worry about that. Beyond that, we can do all of the transformations that we've seen earlier. Horizontal shift, we change x to x minus h. Vertical shift, we add k at the end. When we flip across the y-axis, we change from x to negative x. When we flip across the x-axis, we have a coefficient that's a negative. A vertical stretch or a horizontal stretch, vertical stretch will put in, or stretch or shrink, you put in a coefficient out front. The horizontal stretch, you put in a coefficient in front of x. That's all what we've done previously. One thing about exponential functions is that with exponential functions, there's this interesting base that we use. It's called base e. And e is an irrational number associated with exponential growth. On every scientific and graphic calculator, you'll have a button for this numerical value. It's approximately 2.71828, but it is irrational, so it keeps going on and on and on. It actually comes from a limit of growth, which we may see later. That later will not be in this video, but maybe later on in mathematics, you'll see where this E specifically comes from. So 2.71828, so on and so forth. Again, it's a button on your calculator. And it's very much linked to a continual growth concept. So when we have a situation in real life with continual growth, we'll often see that E show up. So because of its connection to exponential functions, let's use it as a base. Let's try to graph the original base exponential function whose base is E, and then transform that by adding 3 to your x value, and then by subtracting 2 and negating the coefficient in front of the e to the x. So the base function, f of x is equal to e to the x, that's pretty straightforward. It looks like our standard exponential function whose base is greater than 1, since e is that 2.71828 number. You can see that when you plug in 1, what you'll get is that 2.71828 as my y value. Again, that's a rounded number. That's not the exact value of e because e is irrational. When we take e to the x plus 3, that should shift this left 3 units. So my initial point of 0, 1 should move left 3 and bring me to negative 3, 1. Let's see if that actually happens. Sure enough, when I graph that, e to the x plus 3 is just the shifted left version of e to the x. So every point got shifted 3 units to the left. Negative e to the x minus 2, That's going to be a flip across the x-axis because we have a negative in front of e to the x, and then a shift down by 2. So we're going to flip and then shift down 2. So it looks like my initial point of 0, 1 is going to flip. So it's going to go to 0, -1, and then get shifted down 2 units, and that'll go to 0, -3. Let's see if that does. Sure enough, that's what happens. It's a flip and then a shift down by 3. So e to the x is a function just like any other function where our base is bigger than 1. And transformations of e to the x work just like transformations of 3 to the x power, or 5 to the x power, or anything we want to the x power. Now we get to the real reason we're looking at exponential growth. Exponential growth is important because of how it operates. Exponential growth is growth that does like repeated multiplication growth. So we're multiplying over and over and over. And this is what happens if we have percentage type growth happening over and over and over. So imagine that we have money in a bank account and every year it grows by 4%. Well, year 1 it grows by 4%, year 2 it grows by 4%. That's repeated percentage growth over and over and over. And when we say repeated multiplication, we mean every time we increase x by 1, we're going to multiply by another b. That is our base. So let's take a look at this function we've seen earlier, 2 times 1.04 raised to the x power. Or in this case, I put 200 times 1.04 raised to the x power. So let's actually do that instead of 2 times 1.04 raised to the x power. If I were to plug in 0, I'd start at 200. If I were to plug in 1, I would have gotten out 208. If I would have plugged in 2, I would have gotten 216.32. If I would have plugged in 3, I would have gotten 224.9728 approximately. Notice that is basically starting at 200. When you multiply by 1.04, that's like gaining 4%. That's one multiplication by 1.04. When I plug in 2, that's like 2 multiplications by 1.04. So I take 200 times 1.04 and then again times 1.04. So going from 200 to 208 is a multiplication of 1.04. Going from 208 to 216.32 is another multiplication by 1.04. Going from this 216.32 to 224.9728 is another multiplication by 1.04. This is the exact value. So each time we increase our input value by 1, it's another multiplication by 1.04. Now imagine we were saying that we're starting a bank account which has $200, and each year it gains 4%. Gaining 4% would be a multiplication of 1.04. So after year 1, the bank account would have $208 in it. After year 2, the bank account would have $216.32 in it. And after year 3, the bank account would have $224.9728 in it. And this leads us to a really nice exponential function formula. This is the formula for the amount of something we have if we start with amount P and we compound M times per year, having a growth rate of R for T years. If the T is variable and the M, the R, and the P are fixed, then this becomes an exponential function. So the amount that we have after T years is called A. Our initial starting amount is called P. The reason it's called P is because when you're dealing with money, your initial amount is called the principal. So this P is a stand-in for the principal, which is the initial amount. R is the rate of growth, and then M is the number of times we compound per year. That shows up in the denominator here and also in the exponent. And then T is the number of years we are going to observe that type of growth. So if we have percentage growth compounded M times per year, we end up with this formula, which is just an exponential function. Let's do an example. This says to create an equation for the amount in an account if we initially put in $12,000 at 5% growth rate compounding monthly. Once we set up the equation for that, we'll compute how much will be in the account after 10 years and how much will be in the account after 40 years. If we want to create this equation, since we're compounding monthly, monthly is 12 times per year. So that's M equals 12. So monthly is 12 times per year. My initial amount, which we call our principal, is 12,000. So this equation becomes A is equal to 12,000 times 1 plus R over M. We already established that M was 12. Now the only thing to fill in is the R. Since it's a 5% growth rate, that means the R value is 0.05. That's a 5% yearly growth rate. So there we go. Notice what this is an exponential function whose base is 1 plus 0.05 divided by 12. We have this coefficient of 12,000. And the exponent is 12 times t. That's a horizontal shrink there. But it's an exponential function. And then we can ask, well, how much will be in the account after 10 years? How much will be in the account after 40 years? So after 10 years, all we have to do is take this equation and plug in a 10 for my value of t. Now, this is one thing you have to be careful of when you're plugging this into your calculator. 12 times 10 needs to be calculated before we take the exponent. We can't take the exponent of 12 and then multiply it by 10. Sometimes if I'm dealing with a scientific calculator, I will multiply the 12 times 10 first and call that 120 when I type it in to the formula. So make sure the exponent of 12 times 10 gets multiplied before we actually take the exponent. Other than that, it's pretty straightforward. We type it into the calculator, and this gives us out an amount which is in dollars, $19,764 and about 11 cents. I rounded that, but if you were doing this in a bank, the bank would also round it to 2 decimal places. So maybe you can put the approximate, or maybe you can put equal to, it doesn't really matter. The same thing is going to be true after 40 years. After 40 years, what would happen is we just replace the t with a 40, do that same calculation on our calculator, and after 40 years, we end up with $88,301.01. Again, that's a rounded number, but the bank would round it too. So there you go. I want you to notice that we started with 12,000. In the first 7 years, oh, sorry, we started with 12,000. In the first 10 years, we gained about $7,764. So a little less than 8,000. But in the next 30, we gained quite a lot. In the next 30, we went from 19,000, almost 20,000, to about 88,000. That's a much bigger gain than the first 10 years. That's what happens with this compounding interest, that it might start out looking like a fairly slow gain, but after a while, after you wait 40 years, you end up with some pretty big gains. And that's just how exponential functions work. Just to show you that, I've graphed this on an adjusted window, but what we're saying is we're starting out at 12,000 and then it's sort of growing. That first 10 years, the growth goes from here to here. If I looked at the average rate of change, it would look pretty flat. But as we move to 40, that increase starts speeding up. And it continues to speed up the more we go to the right. So the next 20 years after that, we see some really big growth. And after 60 years, we'd be at 239,528.87. So this is the magic of compounding interest. If we just let that money grow for long periods of time, then it starts speeding up over a long period of time. The growth does, the amount we have in the bank does. Let's try another example. Let's create an equation for the amount in an account if we initially put in 1,900 at 2.75% growth rate, compounding quarterly. After you do that, figure out how much is in the account after 10 years and figure out how much is in the account after 40 years. You can push pause on the video and try this on your own. I will show you how it's done in a couple of seconds. All right, the first thing we need to do is realize that compounding quarterly means that we're compounding 4 times per year. So M is going to be 4 in this equation. And compounding quarterly tells me I can use this equation. We'll see another case in the next examples where we're not compounding quarterly, but compounding continuously. So we're compounding quarterly, that's 4 times a year, so I can use this equation. My principal in this case is 1,900. The rate of growth is 0.0275. Make sure you write that as a decimal and not as a percent. If you write it as a percent, then everything gets thrown off. We're dividing by 4 because m is equal to 4, and then my exponent is 4 times t. So that's the equation that I end up with. Now, after 10 years, all we do is replace the t with the number 10. So after 10 years, we'd have 4 multiplied times 10 as my exponent. And I can calculate that on my calculator. I just plug that in. Remember that if you are doing this on your calculator, be careful that your calculator multiplies the 4 times the 10 before you take the exponent. In my case, I got $2,499.06, rounding to 2 decimal places. So after 4 years, we go from 1,900, and we've gained almost $600. Let's see what happens after 40 years. We're not going to gain an additional $600. We're going to gain more than that. We're going to take 1,900 or 1,900, 1 plus 0.0275 over 4, and raise that to the 4 times 40. When I did that on my calculator, I ended up getting $5,686 and about 47 cents. Notice again, after the first 10 years, we've gained 600, but we've gained a lot more after 40 years. By the way, the previous problem had a faster rate of growth. It was at 5% compounded monthly, whereas this one was 2.75% compounded quarterly. By the way, that means an average growth rate. It always looks like it's growing at 2.75% all the time. And we're basically every quarter, so every 4 times per year, we recalculate how much is in the bank. So that's what's happening in this case. But the point is, this was a slower rate of growth than the previous one. And you can see that it doesn't have nearly, it has bigger gains as the time increases, but it doesn't have percentage-wise as much gains because our rate of growth is smaller. So that's how to use this formula. This formula is really important to financial settings. It's really how all of bank interest calculations get made, both on the loan side and on the depositing money side and lending out money and all that stuff. So the question arises, what happens if our growth is not happening 4 times a year, or 12 times a year, or 365 times a year? What if our growth is happening continually? What if it's compounding continually? Well, then the M is just going to get really, really, really big. And it turns out that formula that we had for calculating a percentage growth M times per year, as M gets really, really big, as M goes to infinity, this formula turns into this one with our base E. So we have principal times E to the RT. And if this T is a variable, then this is an exponential function. Continual growth happens fairly often. It's something that occurs in nature a lot. And that's why this E is such an important irrational number. It's because it's the base for continual compounded growth and how that works. It turns out, again, it's about that 2.71828 number. So let's use this in a monetary situation. Let's create an equation for the amount in an account if we initially put in 325,000 at a 5.5% growth rate, compounding continually. And then we'll compute how much we'll have after 10 years, how much we'll have after 40 years. If you want to try this on your own, go ahead and push pause on the video and try it on your own. In a couple of seconds, I will do the problem. All right, the key thing here is that we are compounding continually. So because we're compounding continually, I can use the A equals PE raised to the RT power. In this case, since we're starting with 325,000, that's my principal. And then E is just the irrational number E. The R is 5.5%, which as a decimal is 0.055. And T is my variable because we can let that money sit in the account for any number of years that we want. Hopefully that makes sense. Our R is always going to be the decimal version of the percentage. You can always move the decimal place over 2 spots to get the R from your percentage. Now, after 10 years, what we would do to find how much is in the account after 10 years is we take the 325,000 times E to the 0.055 multiplied times 10. The 0.055 is being multiplied by the 10 inside of the exponent. Make sure that that gets multiplied by the 10 inside the exponent. Once you do that, you should see that after 10 years, you would have $563,307.23. So if you start with 325,000, after 10 years, you end up with 563,000, roughly. After 40 years, we do the same thing. We take this expression and all we do is change the 10 to a 40. The amount we'll have after 40 years, when I calculate this, is about $2,933,129.39. That's rounding to 2 decimal places. So we go from 325,000 initially to almost 3 million after 40 years. After 10 years, we'll have about 563,000. After 40 years, almost 3 million. Again, this is sort of the magic of continually compounding interest, that if you wait long enough on that, the growth becomes really, really big because we're ending up with this exponential type growth. By the way, I know I've just said it's e to this power. On most calculators, you'll have a button that is e to that power. And so you can just hit that button, e to the power, and then type in the exponent there. So there should be an e button on your calculator. There might be an addendum video to this, so an added video to this that shows you where that e button is on your calculator. Now, bank and money calculations are not the only calculations that have continually compounding interest or continually compounding growth. Let's look at another application. Let's say a city currently has a population of 45,320 people. Let's create an equation for the amount of people in the city in the future if we are projecting a 2.1% growth rate compounding continually. And then when we do that, we'll ask how many people will there be in 10 years if the projections hold up? And then how many people would live in the city in 20 years, again, if the projections hold up? So we'll create an equation and then we'll see what's going to happen in 10 years and 20 years if this 2.1% growth rate keeps up. Go ahead and push pause on the video if you'd like to try this on your own. In a couple of seconds, I will show you how this problem is done. All right, so the first thing we notice is that we have a growth rate that is compounding continually. Anytime we're compounding continually, then we're going to be dealing with A equals P e to the RT in some way, shape, or form. Now, officially, I use this equation always, but other people will change up the letters in front. So instead of using P, they'll use A sub 0. That just means initial amount. Sometimes you'll see the letter K instead of the letter R. Those all just mean the same thing. K is a growth rate. A sub 0 is the initial amount. We call that principal. That might not be super appropriate for a population. Principal is a term usually used with money, but we understand that it's our initial amount. And so even with people, since we're starting with 45,320 people, we'll write that in for the P. Again, just other scenarios, they might use a different letter in as the coefficient and a different letter for the rate, but it means all the same thing. My initial amount, 45,320 people. My rate of growth is 2.1%. That's an R of 0.021. And then obviously we have our T, which is our variable. If I want to figure out how many people would live in the city in 10 years, if the projections hold up, I'd say A is equal to that whole thing where I replace the T with the number 10. So we take 45,320 in on our calculator, we hit the E button, raised to the 0.021 times 10, and that becomes 55,910.29 people. Now that may be troublesome for some people for understanding because we have this question of what is 0.29 of a person. Some people would tell you to round that to the nearest whole number because we can't have 0.29 of a person. Other times, people would say this is just a projection, so go ahead and round it to 2 decimal places. And we just know that we can't have 0.29 of a person. So either way is perfectly fine with me. In my class in Moodle, it'll specifically tell you where to round it. Round it to the nearest whole number or round it to 2 decimal places. After 20 years, all we have to do is replace the T with the number 20. This is a pretty easy calculation, same as before. Again, in 20 years, we're looking at 68,975.30 people. Again, if you wanted to make it make a little more sense by rounding it to the nearest whole number, you could do that as well. But that's the idea. So notice that continual growth, when our growth is compounding continually, we end up doing the exact same thing, whether we're talking about people, whether we're talking about money, whether we're talking about any other scenario where we have continual compounding interest. We use this A equals P e to the RT, or whatever letter you want to choose for the P and whatever letter you want to choose for the R, and then plug in the correct values. Let's do another example of population change, but this time we'll throw in a couple of little curveballs. This says a county had a population of 15,800 people in 1980. On average, it has lost 1.5% of its population each year. Create an equation for the amount of people in the county T years after 1980, given that the loss or the decay rate is compounding continually. So in this case, we're losing population, but we're still compounding continually. And we're going to want to start our count at the year 1980. Then we'll say, what do we expect the population, what do we expect the population was in 2005? And what would we expect the population to be in 2040? Obviously, if this keeps up, if this pattern keeps up. If you want to try this on your own, you can push pause on the video now and try it on your own. Otherwise, I'll do it in just a couple of seconds. All right, so the county had a population of 15,800 people in 1980, okay? And we're starting our years count at 1980. So if what we're saying there is that the year 1980 is actually equal, or is, let me rephrase that. The year 1980 means my t value is 0. So t value of 0 represents 1980. We are doing continually compounding interest. Therefore, the A equals P e to the RT is the formula we're going to be using. If we were doing compounded annually or compounded yearly or compounded monthly, then I'd use P times 1 plus R over M to the MT. But compounding continually, P times e to the RT. So if we're starting out with a population of 15,800 in the year 1980, that becomes my principal. Again, principal is a better term with money, but in this case, it works as well. So 15,800, and then losing 1.5% per year means that the rate is a negative 0.015. So anytime we have a loss or a decay, then our R is going to be a negative. So in this case, that's negative 0.015. So this is the equation that we want. The amount is 15,800 times e to the negative 0.015 times t. Then it asks us, what do we expect the population to be in 2005? Remember, our time starts at 1980. So to go from 1980 to 2005 is a difference of 25 years. Just take 2005, subtract 1980. We get a t of 25. And that's what we have to put in for that t value. Then it's a straightforward process of plugging this into our calculator, making sure that the negative 0.015 gets multiplied by the 25 in the exponent. When I did that, I get 10,859.17 when I round it to 2 decimal places. Now, again, this is number of people. So Your book may ask you to round it to the nearest whole number instead of the 2 decimal places because we're talking about people. Other times, because this is a projection, somebody might want just to have the projection with the decimal places. How about 2040? Well, 2040, that from 1980 is a difference of 60. 2040 to 1980 or 1980 to 2040, that's 60 years past 1980. And if you do those calculations, you'll get 6,423.80 people. Notice that 1.5% decline, again, from 1980 to 2005. That was a 5,000 reduction of people. Now going from 2005 to 2040, that's like 4,400, or not, 3,400 reduction in people. Let me do the calculations here. Yeah, 4,400 reduction in people. So we dropped by 5,000 those first 25 years, and then the next 35 years after that, we dropped by another 4,436 people, roughly. So there you go. That's what's happening. Notice that as we're dropping, it's kind of slowing down as we get higher and higher t values. And that's because with decay, the graph is going to be doing something like this. With decay, we're getting a graph that looks like this. We start in the upper left, and as we move right, we move down towards 0. With growth, we get this pattern. You start close to 0, and then you move up and to the right, and it goes up forever. With decay, it looks like this. So that's how we can deal with decay rates. We use decay rates of, when it's a decay rate, we use a negative R value. And then obviously we can start in the year 1980, meaning t equals 0. That would mean t of 25 is 2005. A t of 60 is 2040. With positive growth rates, we're moving up and to the right. With decay rates, we're moving down and to the right. Now, those last 3 examples all dealt with this function with, again, base e. I always use p as my coefficient, and then r as the rate, and then t as my time. Other people may switch that up, switch what those letters are. Instead of using p, r, and t, a is another, A0 is a common letter for p, k is another common letter for r, x is another common letter for t. Now, this is continually compounded interest. The other compounding interest is m times per year. Don't forget both of these. And make sure that when you read a problem, you understand whether we're dealing with m times per year, something like monthly compounding or annual compounding or quarterly compounding, versus continually compounding. These 2 equations are going to be important with any problems in this class dealing with percentage growth. Those are two very common exponential functions. Those are obviously not the only exponential functions. We saw a lot of other exponential functions. Any function that can be written like this is exponential. We can always adjust this as well by translation and things like that. So this ends this section on exponential functions.